Okay, so welcome everyone again to the course in infinity categories and homological algebra. This will be the last lecture, and the plan for today goes as follows. So I will continue with a discussion I started in the end of last lecture on presentable categories, and then I will speak about two other things, which in principle are separate one from another, which are stable categories and localization. And then all of these words will come up when I speak about properties of the derived category of a ring. So let's start at the beginning. I will slightly change the presentation of which I began last lecture on presentable categories. It will mostly be the same, but with some modifications to simplify it. So anyway, let's start. Okay, so first things first, lambda will be a regular cardinal. This means that if I have an indexing set of cardinality less than lambda and a family of sets of cardinality, each of them less than lambda, then the union over I of these sets has also cardinality less than lambda. Okay? For example, if you have a finite union of finite sets, then it is finite. So the first infinite ordinal is regular. Right? Okay, and then notation. So a set is lambda small if its cardinality is less than lambda. And again, notice that aleph 0 small is finite. Okay? So cardinality less than infinite, so to speak. All right. So now we have discussed two examples of categories which were built out of so-called small objects last times. One was a category of sets in which every set is a union of its finite subsets. And the other one was the category of R modules, in which every module is a co-limit of finally presentable modules. And the idea is to give a general definition of categories which can be presented in some way by small objects. Okay, so I'm heading in that direction. Right, and for that I need several definitions, which I'll give one after the other. So first, poset P is lambda directed if every lambda small subset has an upper bound. Okay, e.g., the natural numbers with the usual order is aleph 0 directed. All right, if I take finitely many elements in n, then take the maximum, that's an upper bound. All right. So a diagram is lambda directed if it is indexed by a lambda directed poset. Okay. Yeah, by a diagram, I just mean a functor. So a P-shaped diagram in C is a functor from P to C. And here I'm asking that P is a K directed, lambda directed poset. So for example, each time I have a diagram stemming from the natural numbers, This is an Aleph 0 directed diagram. Okay, so there's a question here in the audience about whether C is a 1 category or an infinity category. For peace of mind, if you're comfortable with it, you can assume it's a 1 category. But kind of the point is, once I finish with the definition, if you replace all definitions by infinity, you get the same. So yeah, P will be, well, it's opposite, so it can be viewed as a 1 category, and then we can view a 1 category as an infinity category. And even in the infinity categorical context, this will still remain a 1 category viewed as an infinity category, opposite. Okay. So if you notice, I changed slightly the notion. I wrote something about filtered co-limits last time. I simplified it because one can. So I'm just working with posets to make the exposition simpler. Anyway, let's move on. But yeah. All right. So a lambda directed co-limit is the co-limit of a lambda directed diagram. Okay. So for example, in set, and for countable, the countable ordinal, the first countable ordinal, well, the only one. Then say a filtering union is an example of such a co-limit. Right. Okay. And so informally, we'll say that, say for sets, for example, that a set will be small if each time you have a map into a directed co-limit, you actually get mapped into one of the factors. So this, for example, happens for finite sets. I'm only talking about unions here to simplify co-limits, but if you have a finite set, I'm up into a union, since the elements are finite and the union is increasing, it will eventually land, the image will eventually land in one of the xk's. You don't really need to take the whole union, right? So this is the notion we're trying to formalize. So we'll say that X in a category C is lambda compact if hom X preserves lambda directed co-limits. And this means that for each directed co-limit, the following map is an isomorphism. Well, actually, an equivalence. In the infinity case, it's an equivalence of anima. So again, if this course was your first exposure to co-limits, then think about the example of unions of sets. What we're saying essentially is that a map into a union is the same as giving a map at some level. Okay, this is more or less the condition that we're asking for. So a map into a co-limit has to factor through some of the factors of the co-limit. Okay, and if you plug in this definition for sets and Aleph 0, you get finite sets, and for modules, you get finally presented. So these were the notions of small we were thinking about in the last lecture. Okay? Right, so before I give the definition of a presentable category, let me check that I'm not missing anything else in the list of definitions I have. Okay, I think not. So definition, an infinity category C is presentable if it's presentable for some lambda. So let's just define lambda presentable. And two conditions have to be satisfied. One is C admits all small colimits. Small means small from some other kappa different from lambda. Colimits indexed by categories which are small in some sense. You can forget about this if you don't know the distinction. It has colimits. And there exists a set S of compact objects so they're small in some sense, which will generate all the others in the following sense. So such that for all, say, Y and C objects, Y is a a lambda-directed colimit of the objects of S. So there is some diagram indexed by a lambda-directed poset, which object-wise takes values in the objects of S, which are some of the objects of C. They're small ones. And if you glue them, you get any other object. So for example, you can, taking unions, write any set as a union of its finite subsets, and the poset of finite subsets is directed. Because if you have finitely many finite subsets, the union is finite. So the indexing poset is directed. Okay? So this captures and generalizes both of these examples we were discussing last time. Sorry, there's a question? Yeah, they're lambda compact, yeah. Yeah, sorry. So let me search for a color here. I don't know if the light will allow it to be shown, but yeah, so lambda appears twice. The generator set is lambda compact, and the colimits are lambda directed. And maybe just one caveat before we move on. So for sets, you can take the collection of all finite sets, and from those, you get any other. But that's not a set, right, in principle? Or at least, well, maybe what I'm trying to say is if you take the set of all finite sets, it's not a set. But what you can do is take S, one representative for each cardinality, right? So up to isomorphism, you can glue everything out of these. Or you can also modify the definition, and instead of being given a set S, you give a collection, but you get a set of isomorphism classes. In any case, you can describe everything in terms of small objects by gluing, and the gluing operation is not too large. That's much intuition as I can say. I don't know. Right, and before moving on, let me just write this down. So set and R modules are presentable. And just a preview of the advantages, formal advantages of presentable categories. So many times we wish to know if a certain functor has an adjoint. For example, one way to prove a category has limits or colimits is to show that the constant cone functor has an adjoint. And we had seen that adjoint functors preserve colimits. Left adjoints preserve colimits, right adjoints preserve limits. So that's a necessary condition. So they have to preserve the gluing in some sense. But for presentable categories, the converse is true. If you want to build an adjoint for a functor, you just need to check that it's compatible with the gluing. Then you automatically get an adjoint. Of course, this may not say much if you haven't seen many examples of adjoint functors, but they're a really important point of the theory of categories and, well, infinity categories as well. So let me just write that down, and then we can pass to the next topic unless there are questions. So if C and D are presentable infinity categories, then a functor is a left adjoint, or what is the same, admits a right adjoint. So this is the left adjoint of some adjunction, which also has a right adjoint, if and only if L preserves colimits for some lambda. Yeah, presentable means lambda presentable for some lambda. Yeah. I mean, I'm asking for both to be, but yeah. Okay. Any questions so far? Is there anything in the chat maybe? Okay. Well, if not, then we can move forward. As I said, perhaps the first part of the lecture will seem a bit disconnected. I'm talking about different topics, and then I'll put everything together, or at least when I speak about the derived category of a ring, I want to say that it enjoys all of these nice properties, which have to exist in the first place. So that's where I'm heading. Right. And okay, so the next one is stability. And yes. The quick answer is, I don't recall, I think it's all colimits. Yeah, well, I mean, a posteriori, it has to be all colimits, because once it's a left adjoint, then it will preserve all colimits. One could nevertheless ask if one can get away with only preserving lambda directed and then getting all colimits. And I think the answer is no, you really need to ask for all colimits, but I might be mistaken. So let me maybe get back to you with that. You can either ask me in person or write me an email, but I don't know the answer off the top of my head. But anyway, so thanks for the question, and sorry I don't have the answer right now. But this is certainly true. That's all I'm trying to emphasize. At least as stated, it's definitely true. Maybe we can do better. That is what I don't know right now. Okay. So as in the last topic, before I tell you what a stable infinity category is, I need to like bombard you with a bunch of definitions. So an object in an infinity category is initial if for every other object, you essentially have a unique morphism. It's not strictly unique. What you ask is that all of these hom anima these are spaces. They have to be equivalent to a point. Okay? So there may be many morphisms, but everything is homotopic to each other. It's like the infinity version of up to a unique choice becomes up to a contractible choice. That's a phrase one encounters frequently. Okay, so if you've seen the definition for one categories, you would be asking this to be the 1-point set with an equal. I'm asking for this to be equivalent to the 1-point space. Okay, and finality, likewise, you only have essentially one map 2x for every object C. And then we say that x is a 0 object if it is both. Okay, so let's just very, very quickly go through some classical examples. So in set and topological spaces, the situation is exactly the same. An initial object is the empty set. There's only the empty function from an empty set to somewhere else. But this is not a 0 object because there are no functions to the empty set. But there's only one function to a 1-point set. Okay? In particular, since these notions will be unique up to equivalence, there are no 0 objects in set because these two are not the same. And any other selection of initial or final will be isomorphic to one another, right? The same situation goes for top. But if you instead have pointed spaces, then now the point is a 0 object. Because if I have any object here, x, comma, little x, a map from the point to here is not a selection of any point of x. It has to respect the base point. So there's exactly one choice that will respect the base point, meaning the only point in x that I selected beforehand. And this is, in fact, something one can do always. If you have a final object, then you can consider a pointed version of your category, and you now have a 0 object. Okay? Essentially in this way. And well, for modules, 0 is a 0 object, as you would expect. Right. So in the presence of some 0 object, there are 4 types of things that you can define. First, each time you have a map from x to y called f, if you take a push out along 0, you call this thing the cofiber. I'll give you an example of what this is in a second. Just let me define it first. And there's a dual notion, which is taking the pullback along a 0 map. Which is called the fiber. And then there are 2 specific examples, which are the cofiber of the 0 map from x to 0. And that's usually called a suspension. And likewise, the fiber of the 0 map is usually called a loop space. Okay, so let me give you examples. So say in our modules, well, loops and suspensions are 0. Because pullbacks and pushouts are either subspaces of 0 times 0, which is 0, or quotients of 0 sum 0, which is 0. Okay, so these two, for our modules, at least as I stated them, as a one category, there's no interesting property there. However, for fibers and cofibers more generally, these are co-kernels and kernels. Okay, so cofiber is co-kernel, and fiber is kernel. Okay. Now, say for an infinity category, such as the one given by pointed spaces, then, well, fiber and cofiber are what they're called homotopy fiber and homotopy cofiber, which is a pre-existing thing, spaces. But maybe I can motivate a little bit suspension and loop spaces. So recall that now in the infinity categorical sense, these are the analogous notion for homotopy pullbacks and homotopy pushouts. So if you remember the homotopy pushout we had last time from the sphere to 2 points, what you would do was taking a cylinder out of the sphere and then gluing 2 points, and that was giving us the 2 sphere, meaning the suspension of the 1 sphere. So if you actually do this definition generally, then you get the usual constructions of suspension and loop space, or a space, which are a standard thing that again pre-existed this definition, of course. Okay. Right. So I think we are ready for the definition. There are many ways, equivalent ways, to define a stable infinity category. I'll give one that takes the least effort from what I've said. It might not be necessarily, I mean, it depends on what you're trying to do, if it's the more convenient one or not. But all I'm saying is if you search for this, there might be other definitions, and most likely if you read a bit in any reference about the topic, you very quickly encounter the equivalences. So an infinity category is stable if it has cofibers, meaning those spans which have a 0 on one end, that co-limit, so the cofiber exists always. In particular, you can always define suspensions, and you can prove that the suspension construction defines actually an end functor. So you map x to the suspension of x, and this can actually be done functorially, because in general, the co-limit construction is functorial. And you're asking for this to be an equivalence. You can also ask for the loop, so to have fibers and the loop functor to be an equivalence, or for each, I think you need to ask for cofibers and fibers, and that each square is a pushout if and only if it is a pullback. All of these notions are equivalent, I think. There's a question. Yes, so with a 0 object. Yeah, thank you very much. Sorry, could you repeat the question? Mm-hmm.
Reduce functors once we have it. If you take C, you have the category.
Okay, I have C, I have sigma. Yeah, you're saying it maybe in this case it's not an equivalence. Yeah.
Once we got it, is the inverse.
Once, yeah, they become inverse to each other. And this is actually, I mean, if you think about it, maybe if we can go over this, diagram. So one of the equivalent definitions is that a pullback is a pullback if it is a pushout. So if you look at these squares, then what you're saying is that, okay, you take X, you define the pushout. By definition, it's a suspension. But this needs to be, by this property, also a pullback. So by definition of the loop space, X now has to be the loop space of the suspension of X. Okay? And in fact, yeah, if you have, let me just make this comment very briefly. If you don't have a stable category, you can then take always a certain limit and stabilize it. So I will say it in a second, but if you have spaces, it's not stable, but you can make spectra by stabilizing in this process.
So there is a canonical map from X to the loops of the suspension.
There's a canonical map from X to the loop space of the suspension. That you always get from the universal property. And it becomes an equivalence. If your category is stable, then it becomes an equivalence, yeah. That's a good question. I have to think about it. But sorry, the question was whether you could equivalently define stable by the fact that there's always a canonical map like this, and whether this one is an equivalence. And again, yeah, the answer is I have to think about it. Maybe it's even obviously true, but something I think I haven't said, maybe I should have, is that all of these topics are actually rather new for me. So. How many times is omega applied? In this construction? Infinitely many times. Yeah, I'm not being very precise. It's just a comment responding to something here in the audience, but yeah, infinitely many times. And this is similar to the fact that, say, if you have an R module and an endomorphism map, it might not be an ISO, but you can always consider the co-limit of apply F, apply F, apply F, and if you insist enough, it becomes an ISO. So here, F becomes an ISO, and in fact, the inverse is just shifting to the left, right? Because if you shift to the left and apply F, you arrive at where you started. So it's like I'm doing a dual notion here because I'm taking loops and limit instead of suspension and co-limit, but it's kind of that idea. If you take loops enough times, and by enough I mean infinitely many, then you get something stable. But anyway, there's no point in saying anything about stable categories if I have 0 examples. And I will give some, but let me defraud you from the beginning. So no one category will be stable. So this makes it, at least if you're not familiar with infinity categories, it's a bit harder to give examples. So no one category is stable. Now, the reason for this is exactly the same as that in modules, which is that this suspension is a certain push out with zeros here. And in one categories, this will be 0 again. And then, so the suspension functor for one categories is the constant functor on the 0 object. And that can only be an equivalence. Sorry?
No one category except the 0.
Yeah, no one category except 0 is stable, sorry. And what I mean is that, yeah, so if you have a 0 object to begin with, then the suspension in the one categorical case is just the constant functor. And that is only an equivalence if the original category you start with is just a 1-point category. Okay? So for most examples, you really need to go to the realm of infinity categories. And maybe right now, it depends on what you know, if these examples are motivating for you. But maybe the point I want to make is that these will appear in the school. I will give you some names you can search for that will appear in the courses. Okay? So, for example, in the first week, we have KK infinity, which is an infinity categorical version of bivariant K-theory. This will be a stable infinity category. Then, well, we'll see today the derived category of a ring. The infinite categorical version. And also, you can replace rings. So instead of modules, consider more functional, analytically flavored modules, so to speak. And all of these things will have stable categories associated to them. And then another thing that will come up many times, or I think it's likely to come up, is the category of spectra, which, as I was saying, is the stabilization of spaces. Okay? And a further point, so maybe you're not familiar with infinity categories, but you've come across triangulated categories. And one of the points of stable categories is that if C is stable and you take the homotopy category, this was a one category associated to C that we defined last time. So objects are the same and morphisms are one morphisms up to equivalence. This is always canonically triangulated. And many triangulated categories of interest, like the classical derived category of a ring, are the shadow of a stable category. And at least when you define a triangulated category, you have to give a category plus extra structure. One advantage, at least aesthetically, but also technically, of stable categories is that being stable is a property. You're either stable or you're not. You don't have to provide any extra structure. So this is something a category either satisfies or it does not satisfy. Okay. It cannot be that you didn't find the right structure to make it triangulated. It's either stable or not stable. All right. Good. Exactly. Yeah. Any other questions on the stability part? Nothing in the chat? I feel like I'm going to say this many times today. So the question was whether the Frobenius category of a ring, sorry, the Frobenius ring, which appears in Hobbies-book and model categories, you said? If this has an infinity categorical model. Again, I'm sorry, but I don't know. But maybe somebody knows in the chat. For example, if Dave happens to be in the chat, there's a high chance that he has an answer. I don't know. What?
He'll let you know.
Okay. Good. Anyway. All right. So again, we now are switching topics, but this is essentially the last thing I need as a prerequisite, which is localization. And the idea for this is that now you have a category and a family of morphisms that need not be isos or equivalents, but you really want them to be. Like if you want to do algebraic topology and you care about spaces up to homotopy equivalents or up to weak equivalents, then you might want to have a category in which you force these things to be isomorphisms. And so there's a standard procedure to do that. Let me briefly tell you how it looks like. And then I can go into chain complexes and the derived category and pay homage to the and homological algebra part of the title. Okay. So anyway, if C is an infinity category and W is a collection of morphisms, then there is an infinity category, which I will call CW minus 1, and the functor from C to CW minus 1. And so the idea is that this functor maps things in W to isos, and it's the smallest thing you can do to transform W into isomorphisms. Okay, so 1 gamma maps W to iso. 2 for every other infinity category D. This functor gamma induces an equivalence. So from functors from C with W inverted to D. So if you have a functor like this, you can always pre-compose by gamma. Now, since the arrows in W get mapped to isomorphisms here, the composition will definitely map W to isomorphisms because functors preserve isomorphism, right? But the point is that if you pre-compose, you get an equivalence between functors from C to D, but not all of them, the ones mapping W to isos. Okay, so yes, so by an iso, I mean it has an inverse up to equivalence. So if a one morphism from X to Y needs to have a morphism in the other direction, and then you ask for both compositions to be equivalent to identities. This is witnessed by a selection of a two morphism between the composition and the identity. Okay. So they're akin homotopy equivalences of spaces, say. Okay. So what this is saying is it's like a quotient type property, right? A functor from C to D passes to C W inverted if you map W to isos. Okay. So it's like localization of rings. Okay. And I think there's about one example I can give you before passing to the derived category part of the talk, which is if you take CW complexes and you invert homotopy equivalences, or you take spaces, all topological spaces, and you invert weak equivalences, then you get anima, the infinity category of spaces. So notice, for example, that these I view as a one categories, but once I localize, they become an infinity category that is not a one category. And in particular, this reminds me of something that I was imprecise about last time. So if you take the homotopy category of anima, now if I'm not mistaken, this should be the homotopy category HCW. You can also take topological spaces, but then you take the homotopy category in the model theoretic sense. So you localize with respect to weak equivalences. And if you take CWs, then the hom sets are really homs modulo homotopy equivalence and not weak equivalence because of CW approximation and Whitehead's theorem. Yeah, so the question was in anima, objects are spaces in the sense that they're weak homotopy equivalent to CW equivalence.
Yeah. In anima, they are homotopy equivalent.
Yeah, well, you can define it in two ways. You can consider all spaces up to weak equivalence. And so objects are topological spaces, but the morphisms are up to weak equivalence, which of course ends up being equivalent by Whitehead's theorem and CW approximation. To inside of it, you get CWs. Everything is equivalent to a CW. And between CWs, you really do get homotopy equivalence. Yes, that's CW approximation. Yeah, isomorphic in the infinity sense. Yeah, exactly. Yeah, in the infinity categorical sense, yeah. Yes, you can stick to CWs. Yeah. Yeah. And well, further, I think, again, I don't want to speak too much about things I'm not entirely knowledgeable about, but I think there's also a further distinction. This has to be thought about the category of homotopy types. So spaces up to homotopy. So you really care about things up to homotopy. Anyway, but yeah, so just to correct my previous mistake, I think the honest way to say this is HCW, or you take the homotopy category of the model category of topological spaces. Okay. Anyway, so and 10 or 15 minutes that I have left. Now, I want to say a little bit about homological algebra and put all of these things into context, or at least into use in one example, which will appear in the course on approaches to functional analysis. Okay, so let's start from the beginning. Chain complexes and the derived category. Okay, so I will fix R a ring and mod R the category, the one category of modules, say on the left. And everything that I will do, if I'm not forgetting anything, you could replace R mod by any Grothendieck abelian category if you know what that means, but I don't want to spend time with the definition because we don't have too much time left. So we can stick to R mod for concreteness. Okay, so let me first recall / define a one category, which is the category of chain complexes. So objects are chain complexes, and these are sequences of modules with maps between one and the next. And they satisfy a condition, which is that if you do a map on the next one, then you get 0. Okay. And then morphisms are a sequence of maps from each Cn to a certain Dn, the nth term of another chain complex. And you ask for these maps to commute with the differentials. So you get a drawing of this sort for each n. Okay. Okay. So the nth homology of a complex is this group, is the kernel of the nth map modulo the image of n plus 1. Now, this image is contained in this kernel because two maps, one next to the other, compose to 0. Now, you might ask, when are they exactly the same, this kernel and this image? So when is this sequence exact? And that's exactly when the homology groups vanish, right? And you might have seen this many times already because, say, let me be informal about this. Many invariants like singular homology, the Ram cohomology, Hochschild homology and cohomology, and so on, can actually be defined as functors from certain category. Now, for each object, say for each space, I have a singular homology complex, and then I take homology, right? So they're typically functors that you can obtain in this way. So you might be losing information when you take homology. You could consider the more fundamental invariant to be the complex itself, okay? So I want to finish with defining a category of chain complexes up to homology in some sense. And this requires a further definition. So what do I mean by this? So a chain map from two complexes, which recall is a bunch of maps level to level, induces maps in all the homology groups. If you've never seen this, this is a nice exercise. And we say that F is a quasi-isomorphism if all of these maps are iso. So F is a quasi-isomorphism if it induces isomorphisms in all homology groups. Warning, this is, two complexes are not quasi-isomorphic when they have the same homology groups. This is the same as weak equivalence and homotopy equivalence for spaces. You really need a map implementing the isomorphisms, and the map has to be the same one for each homology group, okay? But the idea is that many invariants in homological algebra have to do with this derived category that we'll define, which is chain complexes, up to this notion of quasi-isomorphism, okay? Right. Now, given that we've learned how to invert morphisms in an infinity category, and this one category of chain complexes can be thought of in particular as an infinity category, then we'll take the definition to be take the one category of chain complexes and then localize in the quasi-isos. So the derived category of R is taking the one category of chain complexes viewed as an infinity category, localized are the quasi-isomorphisms. Okay. If you take the homotopy category, you get the usual classical derived category. Great. And the last thing I want to say is this theorem, which says that the derived category is a stable, presentable infinity category. So I really needed localization to define it, and I really wanted to say that it enjoys these two nice properties. This explains all the prerequisites that I explained today. Okay, and let me, to conclude, give you a reason, which is part of the statement of this theorem, of why both of these things are true. So the suspension identifies with the shift of complexes. So I take a complex and I shift it all the way to the left, I think. I always get this mixed up, but anyway, it's either one or the other. So the suspension identifies with the shift, and that's definitely an equivalence by shifting to the other direction. So that is morally why this should be stable. And then, while presentable is a more complex statement, but let me only say that the compact objects are perfect complexes. And these are bounded complexes, meaning up to some point, they're eventually zero on both sides. So there are finally many modules. And each term is finally generated and projected. Okay. So the small complexes are complexes that are bounded, and in each term you get a nice, also small module. And with these, you can actually glue things and get all the rest. Okay. And this was the last thing I had prepared for, so we can conclude with this. Questions?
When you say that the operator is protocol, you need to say like it's lambda protocol for lambda. The lambda is like at 0.
I think so, yeah. Yeah.
Perfection is not just the coherency requirement. Either.
So, sorry, say that
So
again.
perfect.
For me, it's a bounded complex, so yeah.
Theory.
Yeah, the category is if all unbounded. Yeah.
The compact objects.
Yeah, the compact. Yeah. And you can also, again, I don't want to speak about things I don't know much about, but there's a distinction, of course, of whether you take bounded complexes to one side or the other. I think, roughly speaking, this has to do with the requirement of the underlying category being Grothendieck abelian or not. In this case, we don't see the distinction because we have our modules. But say, for example, if I'm not mistaken, maybe you really know about this. If you take unbounded complexes and you want to put a model structure on it, on an abelian category, you need some hypothesis. Whereas if it's bounded to one of the sides, I think it's easier, right?
I think you do it like with
Okay, maybe.
But yeah, so perfect complexes generate all.
Yeah, perfect complexes. Yeah.
So they act as the CW.
Right. Yeah. In some sense, yeah. So these are the nice spaces which you can get once you glue, you get all the others. Yeah. So in that sense, yeah. Any other questions? Okay. So if there are no further questions in the chat, then we can maybe stop here.